Hello, thank you for being here. My name is Sumin Ho from Urban Robotics Lab in KAIST. Today I will be introducing our paper eCDT, which stands for Event Clustering for Simultaneous Feature Detection and Tracking. Our paper tackles the problem of visual tracking in a novel sensor called the event camera. It is a new sensor that detects light intensity changes in its pixels that are output as signals called events. One feature of these events is that they encode whether the event occurred due to a positive or negative change of intensity. A positive change creates an on event and a negative change creates an off event. So an event contains the XY pixel coordinates, the timestamp t, and the polarity p. Conventionally, the red points are on events and the blue points are off events. The contributions of our paper are threefold. We propose eCDT, which allows simultaneous feature detection and 2 tracking by performing a novel clustering approach in the spatio-temporal domain. The novel clustering method called KNN classifier-based spatial clustering application with noise, or KCSCAN in short, clusters adjacent equipolarity events, while it also segregates the clusters of opposing polarity events. By finding continual cluster tracks using cluster descriptors, eCDT shows about 30% longer tracking compared to the state-of-the-art event tracking algorithm HASTE. This is the overview of the proposed algorithm. Raw on and off events in the spatio-temporal 3D space are clustered by KCSCAN. Then the clustered equal polarity events are elongated by head and tail matching, which is HT matching in short. The resulting clusters are called eCDT clusters, from which we extract the feature tracks. First, we introduce what KCSCAN attempts to do. We created an image of the event data within a small time window to illustrate this. If we zoom into a small region in the image, we notice that red and blue dots cluster together. Another key insight is that opposite polarity points could act as barriers to separate equal polarity points even if they are geometrically close. Hence, A, a cluster of on events, B, a cluster of off events, and C, a cluster of on events can be separated. Cluster B acts as a barrier and divides cluster A and cluster C into 2 separate clusters. KCSCAN is a hybrid of 2 famous algorithms, dbSCAN and KNN classifier. dbSCAN stands for density-based spatial clustering of application with noise. As its name suggests, it clusters by density. A point belongs to a cluster if it is a core point, which is when a particular point has endpoints within a radius of R. Similarly, we cluster points, but we define core points using KNN classifiers. A core point in KCSCAN is when the percentage of k-nearest neighbor events within a radius exceeds a core point threshold percentage. Take, for example, points A and B. Points A is an off event, where all 12 neighboring points, including itself, is off. Therefore, point A is a core point. However, point B is not a core point since only 4 points are the same polarity, and 33% do not exceed 75%, which is the threshold value. The final clustered result is shown in D. We can see that although off events exist all over the region, the on events acts as barriers that separate cluster 1 from cluster 3. As described previously, the raw events, which is in figure A, are clustered by KCSCAN that results in segmentations of clusters as shown in figure B. And looking into figure B, we can notice that there is a horizontally abrupt discontinuity in the clusters. The reason for this discontinuity becomes obvious as we look back into the raw events in figure A. We notice a polarity inversion which is caused by the camera moving in the opposite direction. eCDT clusters as shown in C is obtained by connecting these disconnected clusters due to the polarity inversion. Thus, elongating these clusters or reconnecting these clusters are done by a descriptor matching method called head and tail matching, which will become obvious soon. HT matching is performed by first defining the descriptors of the head and the tail of a cluster. The head and tail are defined as the set of event coordinates that occurred within the first or last delta t seconds of a cluster. Then the descriptor of the head and tail is simply the 2D binary image of the coordinate pixels that produced an event. tail descriptors of a cluster is compared to adjacent head descriptors to find a match. A match is found when the intersection over union goes over a predefined threshold value. While eCDT clusters are not primarily point features, for comparison purpose, we extract the cluster center with a moving time window. To evaluate our algorithm, we use a dataset provided by ETH in a paper called the Event Camera Dataset and Simulator. One thing to note is that this dataset provides 6 DOF camera poses at 200 Hz from an OptiTrack system. As shown below, there are 3 scenes in this dataset. From left to right, they are called shapes, posters, and boxes. Since we know the ground truth camera poses at 200 Hz, we use bundle adjustments to find the 3D point of a feature. The feature point is then reprojected back to 2D points to calculate the reprojection error. We found that our method showed, on average, 30% longer feature ages. Table 2 shows that our method was superior in all cases except for one. While we had longer feature ages, the reprojection error were at par with the state-of-the-art method haste. 4 of the 9 cases showed smaller reprojection errors for our method, which means 5 of the 9 cases hasted better. A student t-test revealed that the difference of reprojection errors between each method was insignificant to conclude which is better. These are 2 videos showing the tracks from haste and our method. While haste showed more stable motion, our method is more turbulent. This is mostly due to the events being sparse in the event cluster we create. The sparsity induces fluctuations in the track extraction process. Thank you for listening.